Welcome to DAR Tutors for online and home tuition. In this video, we will explore Chapter 14 of the IBAI-HL syllabus, focusing on affine transformations. This chapter builds a fundamental framework for understanding how to manipulate geometric objects in a coordinate plane. By the end of this session, you will be able to, first, represent basic affine transformations, such as translations, rotations, reflections, stretches, and enlargements, using matrix notation. Second, combine these basic transformations through matrix multiplication to create complex composite transformations. Third, and crucially, you will learn the relationship between the determinant of a transformation matrix and the change in area of an object. This is a powerful tool for solving problems involving geometric areas. And finally, we will investigate how affine transformations are used in fractal geometry by studying the Sierpinski triangle. This will provide a practical application of the concepts. The chapter's content is designed to provide you with a comprehensive and rigorous understanding of these geometric principles. Let's begin by introducing the core concepts. Before we delve into specific transformations, let's establish the general framework. We consider how a point in a 2D Cartesian plane is moved from one location to another. Let's say we have an object point P with coordinates x, y. We can represent this point as a position vector, which we'll call x. After a transformation, this point moves to an image point P' with coordinates x', y', represented by the image vector x'. The relationship between the object vector and the image vector defines the transformation. A very important type of transformation is a linear transformation. It's described by the matrix equation x' equals a times x, where a is a 2x2 matrix of coefficients. This type of transformation preserves the origin, meaning the point, 0, does not move. This simple structure allows us to represent rotations, reflections, and stretches using matrix A. A more general type is an affine transformation, which includes all linear transformations but also allows for translations. The equation is x' equals a times x plus b, where b is a 2D translation vector. This means the origin can now be moved. It's important to remember that all linear transformations are also affine transformations. But the reverse is not true. The vector b simply shifts every point after the linear transformation a is applied. With this foundation, we can now analyze different types of affine transformations. Our first affine transformation is a simple one: the translation. When you translate an object, every point on the object moves the exact same distance in the same direction. This movement is described by a translation vector, let's call it b, with components e and f. This means each x-coordinate moves e units and each y-coordinate moves f units. So, if a point xy is translated by vector b, its new coordinates x', y', are simply x plus e and y plus f. In vector form, the image vector x' is the sum of the object vector x and the translation vector b. Notice how this perfectly fits the affine transformation form x' equals a, x, plus b, with the matrix A being the 2x2 identity matrix, 1, 0, 0, 1, which doesn't change the vector x. Let's work through an example. Suppose we want to find the object point P that, when translated by the vector 2, 3, results in the image point P', 1, 3. So we know the image, P', and the translation vector B, and we need to find the original point, P. The fundamental equation is the image equals the object plus the translation vector. To find the object, we can rearrange this to say the object equals the image minus the translation vector. Substituting our values, the object vector x is equal to the image vector, 1, 3, minus the translation vector, 2, 3. Performing the subtraction, the x-coordinate is 1 minus -2, which is 1. The Shua y-coordinate is 3 minus 3, which is 0. Therefore, the object point was 1, 0. This example shows how to use the translation vector to find an object point given its image. We've successfully met our first objective of representing and applying a basic affine transformation. Next, let's explore rotations about the origin. A rotation matrix will allow us to spin points around the center of our coordinate system. Our goal is to derive the matrix for an anti-clockwise rotation about the origin through an arbitrary angle, theta. Let's start by considering a general point P with coordinates x, y on the Cartesian plane. We can represent this point in polar form. If r is its distance from the origin and phi is the angle it makes with the positive x-axis, its complex number representation is x plus iy, which equals r times cis phi, or r times e to the I phi. Rotating a point by an angle, theta is equivalent to multiplying its complex number representation by the complex number cis theta, or e to the I theta. So, the complex number of the image point, x prime plus iy prime, is the complex number of the object point times cis theta. Now we convert this back to Cartesian form by expanding it using Euler's formula. The image is r cis of phi plus theta. Expanding this gives us the real part x prime and the imaginary part y prime. We can rewrite r saus phi ici as x and r sin phi as y, which leads to the expressions for x prime and y prime. We can write these two equations in a single matrix form. This gives us the transformation matrix A for an anti-clockwise rotation about the origin by angle theta. It's a useful property to know that the determinant of this matrix, cos squared theta plus sin squared theta, is always 1. Knowing this matrix is a cornerstone for solving rotation problems. We have now rigorously derived the formula for a rotation. Let's apply the rotation matrix to a specific example. We need to find the transformation matrix for a clockwise rotation about the origin through 2 pi over 3. First, a clockwise rotation through an angle theta is equivalent to an anticlockwise rotation through the negative angle, minus theta. So, our clockwise rotation of 2 pi over 3 is the same as an anticlockwise rotation of minus 2 pi over 3. This means we will use theta equals minus 2 pi over 3 in our matrix formula. The general matrix is cos theta, negative sin theta, cos theta. We substitute our value for theta. Cos of minus 2 pi over 3 is negative 1/2. Sin of minus 2 pi over 3 is negative square root of 3 over 2. Plugging these values into the matrix, paying close attention to the negative sign on the sin theta term, gives us the final transformation matrix A. This matrix will transform any point by rotating it clockwise through an angle of 2p over 3. Now let's work backward. Given a transformation, we need to find its nature. Consider the equations x prime equals 3x or 4y over 5 and y prime equals 4x plus 3y over 5. Our first step is always to convert these into a matrix equation, which gives us matrix A. The determinant of this matrix is 1, a key indicator that this is a rotation. The general form of a rotation matrix, A, B, B, A, matches this matrix perfectly. So we are confident it's a rotation. To find the angle, we equate the matrix entries to the general rotation matrix formula. We see that cos theta is 3/5 and sin theta is 4/5. Since both values are positive, the angle theta must be in the first quadrant. To find the angle, we can use the arccos of 3/5, which gives an angle of approximately 0.927 radians. So, the transformation is an anti-clockwise rotation of 0.927 radians about the origin. We have now seen how to construct a rotation matrix and how to identify a transformation as a rotation. Our third fundamental transformation is reflection. A reflection flips an object across a line called the mirror line. Let's work to find the matrix for reflecting a point across a general line y. Y equals tan alpha times x. This line passes through the origin and makes an angle alpha with the positive x-axis. Again, let's use polar coordinates. An object point P has angle phi, and its image P prime has angle 2 alpha minus phi. We can write the image vector using complex numbers. The image, x prime plus iy prime, is r cis of 2 alpha minus phi. Expanding this using trigonometric identities gives us the real part x prime and the imaginary part y prime in terms of x and y. These two equations translate directly into the transformation matrix for a reflection. It is cos 2 alpha, sin 2 alpha, sin 2 alpha, negative cos 2 alpha. The determinant of any reflection matrix is negative 1. This value is a unique signature for reflections, which is very useful for identification. Let's see this in action. We'll find the matrix for reflection in the line y equals 3x. The slope of the mirror line is 3, so tan alpha equals 3. We can use the double angle identities to find cos 2 alpha and sin 2 alpha. Cos 2 alpha is 1 minus tan squared alpha, over 1 plus tan squared alpha, which is negative 4, 5. Sin 2 alpha is 2 tan alpha over 1 plus tan squared alpha, which is 3 to 5. Substituting these into our matrix formula gives the transformation matrix. Now let's go the other way. We'll identify the transformation from the equations. X prime equals 3x 4y over 5, and y prime equals 4x plus 3i over 5. The matrix A has a determinant of negative 1, immediately telling us it's a reflection. The matrix form matches a reflection matrix where cos 2 alpha is 3, 5, and sin 2 alpha is 4, 5. This tells us the angle 2 alpha is in the third quadrant. To find the angle of the mirror line alpha, we need the tangent of 2 alpha and the tangent of alpha. Tan of 2 alpha is the ratio of sin to cos, which is 4, 3. Since 2 alpha is in the third quadrant, its angle is p plus arctan 4 to 3. The angle of the mirror line alpha is half of this. To find tan alpha, we use the half-angle formula for tangent, tan x is 2, equals 1 minus cos x over sin x. Plugging in our values gives tan alpha equals 2. The transformation is a reflection in the line I equals /2x. We have now seen how reflections are represented by matrices with a determinant of negative 1 and how to find their mirror lines. Our next transformation is a stretch. Stretches scale an object along a specific axis. A horizontal stretch with a scale factor k moves a point, xy to kxy. Its distance from the y-axis is scaled by k. The matrix is k0, 0, 1. The determinant is k. Similarly, a vertical stretch with a scale factor k moves a point to x, ki. Its distance from the x-axis is scaled by k. The matrix is 1, 0, 0, k. The determinant is also k. Finally, we have an enlargement. This is a special type of stretch that is uniform in all directions. In an enlargement, a point, xy, is moved to kx, its distance from the origin is scaled by k. The matrix is a scalar matrix, ki is 0, 0, k, and its determinant is ki squared. If the scale factor k is between 0 and 1, we call this a reduction. An important point to remember is that an enlargement is a composite transformation. It's equivalent to a horizontal stretch with scale factor k, followed by a vertical stretch with scale factor k. The product of the two stretch matrices gives the enlargement matrix. This highlights the concept of composite transformations, which we'll explore next. Now we move on to composite transformations. What happens when we apply one transformation after another? If we apply a transformation with matrix A to a vector x, we get x. If we then apply another transformation with matrix B to the result, we get B times x. The beauty of matrix algebra is that we can group these matrices. B times x is the same as the product of B and A times x. This means the composition of two linear transformations is itself a single linear transformation, with a new matrix that is the product of the individual transformation matrices. It is absolutely crucial to note that the order matters. BA is generally not the same as AB. The first transformation in the sequence, which is applied to the original vector x, is placed on the right. The second is on its left. This is a common source of error. Let's work through a full example. Find the single transformation equivalent to an anti-clockwise rotation about O through pi over 2, followed by a reflection in the line y equals 2x. First, we need to find the matrices for each transformation. The rotation matrix, which we'll call A, is simple. Cos pi 2 is 0, and sin pi 2 is 1. For the reflection in the line y equals 2x, tan alpha is 2. Using our double angle formulas, secas 2 alpha is 3, 5, and sin 2 alpha is 4, 5. This gives us the reflection matrix B. Now the first transformation applied was the rotation A, so it goes on the right. The second was the reflection B, which goes on the left. We need to calculate the matrix product BA. Multiplying matrix B by matrix A gives us a new 2 by 2 matrix. The determinant of this composite matrix is the product of the individual determinants, Pashonkikita 1 times 1, which is 1. A determinant of a 1 tells us this composite transformation is a single reflection. We can find the mirror line by solving for the new angle alpha, which turns out to be y equals 1/3 x. This example beautifully illustrates how to find a single matrix that combines multiple transformations, and how the properties of the individual matrices can help us identify the final outcome. We've now reached the 10-minute mark. Before we continue with the lesson, I want to take a moment to mention DAR tutors. If you're finding this video helpful and are looking for expert personalized support in your IB A-level or IGCSE studies, DAR tutors can provide that. Our experienced educators are dedicated to helping you master challenging topics like this. For expert tuition, whether online or in-home, please contact DAR tutors. You can find our contact information on our website, dartutors.com. Let's now continue with our lesson on affine transformations. Our next big topic is one of the most powerful connections in this chapter. Our next goal is to understand the connection between the determinant of a transformation matrix and the change in area of an object. This is a very elegant result. To explore this, we will use a simple, well-defined shape, the unit square. The unit square has vertices at the origin 0, A1000, B1001, and C01. Its area is 1, which will serve as our base object area for comparison. Let's apply a transformation to this square and see what happens to its area. We'll use a shear parallel to the x-axis with a factor of 2. The transformation matrix is A equals 1, 2, 0, 1. We apply the matrix A to each vertex of the unit square. O maps to O, A maps to A prime, 1/1000. C maps to C prime, 2/1, and B maps to B prime, 3/1. The unit square has been transformed into a parallelogram. Let's find its area. The base of the parallelogram, the segment O prime A prime, has a length of 1. The height of the parallelogram, the vertical distance between O prime A prime and B prime C prime, is also 1. The area of a parallelogram is base times height, so the area of the image is 1 times 1, which equals 1. Interestingly, the area has not changed. Let's compare this to the determinant of our transformation matrix. The determinant of A is 1 times 1 minus 2 times 0, which is 1. The determinant is 1, and the area ratio is 1. This is not a coincidence. This investigation leads to a powerful and fundamental theorem in linear algebra. For any affine transformation x prime equals a x plus b, the area of the image is the area of the object multiplied by the absolute value of the determinant of a. The determinant acts as a scaling factor for area. Translations, the vector b, do not change the area, only the position. Stretches change the area by a factor of k. Enlargements change the area by k squared. Rotations and reflections, which have determinants of 1 or centre 1, do not change the area. This theorem is incredibly useful for solving area problems quickly and accurately. A key property of linear transformations is what happens to special vectors known as eigenvectors. Let's briefly discuss this concept. An eigenvector of a transformation matrix. A is a non-zero vector that only changes in magnitude when the transformation is applied. Its direction remains unchanged, or is reversed. In other words, if V is an eigenvector, then AV equals lambda V, where lambda, called the eigenvalue, is a scalar that tells us how much the vector is stretched or shrunk. What does this mean geometrically? It means that a point on the line containing an eigenvector will remain on that same line after the transformation. For a reflection, the mirror line itself is made up of eigenvectors with an eigenvalue of 1, because every point on the mirror line stays put. A rotation matrix in general does not have any real eigenvectors or eigenvalues. Why is this? Because a rotation changes the direction of every single vector, unless the rotation is a multiple of 180 degrees. If you have an eigenvalue of 1 or -1 for a rotation, it means the entire plane is filled with eigenvectors. This happens only for rotations of 0 or p. This connection between eigenvectors and the geometric nature of transformations is a powerful analytical tool in higher mathematics. Let's apply these ideas to a fascinating field, fractal geometry. We'll revisit the Sierpinski triangle from the opening problem. The Sierpinski triangle is a classic example of a self-similar fractal. It's built by applying a set of rules repeatedly. These rules are affine transformations. A fractal can be generated from an iterated function system, or IFS. The Sierpinski triangle uses a set of three affine transformations, F1, F2, and F3, to map a larger triangle, OBD, onto three smaller triangles within itself. The process starts with a large equilateral triangle, say OBD. In the first step, this triangle is scaled down by a factor of 1/2 and then translated to three specific locations. Let's find the transformation for the bottom left triangle, F1. The transformation F1 maps the triangle OBD to the triangle OAE. The coordinates show this is a reduction by a scale factor of 1/2 ASOTS centered at the origin. So the matrix A is 1 tau 0 0 1/2. Since the origin O is mapped to O, the translation vector B is 0. The transformation F2 for the bottom right triangle ECD would also be a reduction by 1/2, but it's translated by the vector E 2 0. The transformation F3 for the top triangle ABC is also a reduction by 1/2, translated by the vector A 1 square root 3. We can represent these three transformations with their matrix equations. To get the fractal, we apply this set of transformations to the resulting smaller triangles, and then to the even smaller triangles, over and over again, indefinitely. Let's think about the area of the Sierpinski triangle. Suppose the original triangle has area A naught. Each step removes the central triangle, leaving 3/4 of the area. The first iteration has 3/4 of the original area. The second iteration has 3/4 of that, so 3/4 squared of the original area. The area forms a geometric sequence. As we repeat the process an infinite number of times, the area approaches 0. This is a remarkable property of many fractals. They are objects with dimension between 1 and 2, but they contain an infinite boundary within a finite space, and yet they have 0 area. Now, let's test your understanding with 5 IB-style practice questions. I'll present each question. You can pause the video to work through it, and then I'll provide a fully worked solution. Question 1. A vertical stretch with scale factor k, where k is positive, followed by a reflection in the x-axis, gives the same result as a rotation of pi about the origin. Find the value of k. Pause the video now to attempt the question. Let's work through it. First, we write the matrices for each transformation. The vertical stretch, S, is 1 0 0 k. The reflection in the x-axis, R, is 1 0 0 1. The rotation of pi, t, is 1 0 0 1. The problem states that the stretch followed by the reflection is equal to the rotation. Remember, the first transformation, S, goes on the right. So we have the matrix product RS equals T. Multiplying the matrices, we get 1 0 0 k on the left side. Equating this to the rotation matrix, we see that 1 must equal 1, which is impossible. This means the question statement is incorrect. A vertical stretch followed by a reflection can't be equivalent to a rotation of pi. Let's assume the question meant a vertical stretch followed by a reflection in the y-axis, for which the matrix is 1 0 0 1. If we use a reflection in the y-axis, the composite matrix is 1 0 0 k. Now, when we equate this to the rotation matrix, we find that 1 equals 1 and to k equals 1, which means k equals 1. This result makes much more sense. The composite of a vertical stretch by 1 and a reflection in the y-axis is the same as a rotation of pi. Let's assume this was the intended question, and the answer is k equals 1. Question 2. The affine transformation x prime equals ax plus b, where A is the matrix, 1 to 1, 1 to 1, and B is the vector, 1, 1, maps the unit square to an image. Describe the nature of this image and find its area. Pause the video and try to solve it. Let's find the image of the 4 vertices of the unit square. We apply ax b to O, A, B, and C. The original 4 vertices have been mapped to only 2 distinct points. A prime and C prime are both at the origin, and O prime and B prime form a diagonal. This transformation has compressed the entire square into a single line segment. The image is a line. Geometrically, the image is a line segment, specifically the segment connecting the origin 0, 0 to 1, 1. To find the area of this image, we use the determinant. The determinant of matrix A is 1 times 1 minus 1 times 1, which is 1 minus 1, or 0. A determinant of 0 indicates that a shape's area collapses to nothing. Therefore, the area of the image is 0, which is consistent with the image being a line. The determinant 0 is a critical indicator of this collapse. Question 3. A point P, located at 3, 2, is first reflected in the line y equals x, and then the image P' is rotated 90 degrees clockwise about the origin to get P double prime. Find the coordinates of P double prime. Pause and try this problem. We'll solve this in 2 ways. First, step by step. Reflecting 3, 2 in the line y equals x swaps the coordinates, so P' is 2, 3. A 90-degree clockwise rotation of xy gives yx, so P double prime is 3, 2. Now let's use a composite matrix. The matrices are A equals 0, 1, 1, 0 for the reflection, and B equals 0, 1, 1, 0 for the rotation. The composite transformation matrix is BA, since the rotation was the second operation. The composite matrix M is 1, 0, 0 to 1. When we apply this matrix to the point P3, 2, we get the vector 3 to 2. The coordinates of P double prime are 3, 2. The matrix M, 1, 0. 1 is the matrix for reflection in the x-axis. So reflecting in y equals x, then rotating 90 degrees clockwise is equivalent to a single reflection in the x-axis. Question 4. The quadrilateral ABCD with vertices A11, B51, C54, and D14 is transformed by the matrix 3, 0, 0, 2. Find the area of the image. Pause the video and calculate the area. To find the area of the image, we only need 2 things: the area of the object and the determinant of the transformation matrix. The object is a rectangle with vertices A1, B5 C54, D1004. Its base is 4 units and its height is 3 units, so its area is 12 square units. Next, we find the determinant of the transformation matrix M. The determinant is 3 times 2 minus 0 times 0, which is 6. Finally, we use the area theorem. The area of the image is the absolute value of the determinant times the area of the object. So, the area of a prime, B prime, C prime, D prime is 6 times 12, which equals 72 square units. Notice we didn't need to find the coordinates of the image vertices at all, saving a lot of calculation time. Question 5. Find the single transformation equivalent to a reflection in the line y equals x, followed by a reflection in the y-axis. State the matrix and describe the transformation. Give it a try before watching the solution. First, we get the 2 individual transformation matrices. The reflection in y equals x has a matrix A. The reflection in the y-axis has a matrix B. The problem states, reflection in y equals x is followed by reflection in the y-axis. So the first matrix applied to the vector, A, goes on the right and B goes on the left. The composite matrix is BA. We calculate the matrix product BA. The resulting matrix is beta 0, 1, a 1, 0. Now we need to describe this matrix. Let's look at its determinant. The determinant of M is 0 minus 1, which is 1. A determinant of 1 tells us it's either a rotation or a horizontal shear. The form of this matrix, ABBPE, is a rotation matrix where cos theta is 0 and sin theta is 1. This corresponds to an anti-clockwise rotation of 3 pi over 2, or a clockwise rotation of pi over 2. So, the composite of a reflection in y equals x and a reflection in the y-axis is equivalent to an anti-clockwise rotation of 270 degrees about the origin. We've shown how combining 2 reflections can produce a rotation. Let's summarize what we've accomplished in this video. We started with the general framework of affine transformations. X prime equals ax plus b, which includes linear transformations. We derived and applied the matrix equations for translations, rotations, reflections, stretches, and enlargements. We also learned the crucial process of composing transformations. By multiplying their matrices, we can find a single matrix that represents a sequence of operations, and we saw why the order of these operations matters. Finally, we discovered the powerful area theorem, which connects the determinant of the transformation matrix to the change in area of an object. And we saw a real-world application of these concepts in the study of fractals. Mastering these concepts is essential for success in IBAIHL. This deep understanding of matrix transformations allows us to solve a wide variety of problems in geometry and beyond. Thank you for watching. A final reminder. If you're looking for expert personalized support in your IB, A-Level, or IGCSE studies, please contact DAR Tutors. Our dedicated educators are ready to help you succeed. You can find our contact information and learn more about our online and in-home tuition services on our website, dartutors.com.